it's a good opportunity for us, Yole, to present our work. So we have the marketing side, the technology trend, market trends. But I think for the past 2 days or 3 days, we have a lot of technical presentation, a lot of in-depth technical insights. So now it's a good time to have some market side of the PowerElec and the PowerSiC. So I'm Taha Ayari, so I'm an analyst at Yole Intelligence, and I'm part of the compound semiconductor team where we study, so we can see the PowerElec, PowerSiC, but not only that, we also have RF-GaN, we have photonics, compound related material like gallium arsenide, and we also cover emerging materials as we call like gallium oxide, aluminum nitride, and phosphate. Okay. So I see that like you have there is a lot of PhD students present here, and most probably they didn't hear about Yole, so they don't know what we do and who we are. So I will be presenting Yole Group in a couple of slides, like 6 slides to present Yole Group. Then I will move to the focus of this presentation, where I will have an outlook and give you an outlook of the power electronics, like the mega trend of power electronics industry. Then I will focus on the PowerSiC and PowerElec. As you can see, I will split in the same way. So I will speak about the market forecast, the market trends, application, and the ecosystem supply chain. So who are the players, how the ecosystem is structured, which are the most dominant business model in each material. And I will finish with some technology trend, because it's has been well covered with the previous presenters. And then, for sure, I will conclude with some takeaways and comments. Yes. So it's Yole Group now, because it's composed of 3 companies. So there is Yole Intelligence, where I belong now. At Yole Intelligence, we do market research. We assess the supply chain. We have also activity in M&As and evaluation of companies in the case of due diligence. We have also analysts that can support the community with insights, with the market forecast, so all these activities. Besides that, we have Yole System Plus. In this company, the main activity is what we call the reverse costing. So reverse costing means tear-down analysis with costing models. So for example, we take a Ghent device, we do some cross-section, we look at it through SEM, we try to get back to the process, so how this device is made with costing models. So we have in-house costing model to have the cost of the material, the process of this device. And of course, we have the comparative analysis, because we make tear-down of the different many devices, and at some point we compile this analysis in one report comparatively. And the third entity at Yole is called ECSEL, which is more focused on photonic design and characterization. So at Yole, what we do, that we cover all which is related to semiconductor. So we have the division called Power and Wireless Division, so I highlight it because I belong to this division. But we have also a division that study photonic aspects, sensing, display. We have also groups that deal with packaging, semiconductor manufacturing, memory, the computing and software. And we have also an entity which more focusing on emerging technology. I can say, for example, like quantum technologies. We have colleagues that follow this technology and what we call emerging technologies. So Yole Group, can you see it's relatively a small group. So we have like 180 people compared to 1,000 of like Bosch, hundreds of thousands of people. But we have a strong worldwide presence. So we are present in like 3 continents. Our headquarters, Yole Group, is Lyon, but we have offices in a couple of places in Europe. We are present also in Asia, and of course in the US. So we are present whenever the client is here. So that's a snapshot of our products and what we offer for the semiconductor industry community. So we have the reports. Yearly reports that you can have like updated yearly. that have the structured the same as they will structure the part next, so the technology trend, the market trend, supply chain and technology trend. So we have the monitor, which is a quarterly updated service with the direct access to analysts. So the client that have the access to monitor, they can have the unlimited access to analysts to have more insight, to have calls, to have exchanges. And then the tracks here we have, it's more coming from Yole System Plus. So it's where we have all this step down and you have access to all the step down. As you can see, we cover a lot of different of topics and type of system. And then lastly, we have the custom service. So at some point, then sometimes some clients, they don't find their needs in the out-of-the-shelf reports. So they have specific topics or specific analysis. So in this case, we go to the custom service and we define a proposal, we define the needs of the customer, and we can conduct a specific or custom study to some clients. So that's slide, it's explain our methodology and how we come up with all this analysis, all the forecasts. So for sure, we don't have a crystal ball that we use. So we try to make a solid methodology to come up with the forecast. Here we we have what we call the bottom-up and top-down approach. So bottom-up approach is the approach to where we conduct calls and we talk with the industrial player to get the info, to get the revenues, to know about the technology. And then the top-down approach, so we start with the end system database. For example, internally we have the database, how many smartphones are sold, how many cars are sold. So we start with this database and we go down to the device level, to the wafer and epi wafer. Like we have the model and implementing parameters like the yield, the die size, the penetration of the technology in each application. We can come up with the market revenue and the marketing units. And of course, the idea at the end is to match between the bottom up and the top down. So with the top down, you get a market size, and with the top down, we get also market size by aggregating the different revenue, for example, in the power GaN industry. And then we need to have a match between these two approaches to get the most accurate or objective view on the market. So here we have access to the, as I said, so we have access to a wide base of players in the community. So we are here since now 25 years, and we are a trusted third party, so we can conduct calls with people. And people know us in the community, in the industry, so we know how to aggregate sensitive data and how to deal with sensitive data. And of course, so I spoke about like the Yole System Plus activity. So here comes the Yole System Plus part, where we get, for example, we need the die size. So from where we can get the die size, it's from the chip down from System Plus. So power SiC, we need really the SiC die size to get how many, to know how many from the wafer, we know like the potential good dies per wafer. All these aspects that we feed in our model comes from the work that Yole System Plus is doing. Anyway. So that's just a quick overview of with quantitative and numbers what we have done now. Sounds what we have done since like here it's 20 years, but it's 25 years now plus. So now let's move to the core of this presentation. So let me start with the power electronics overview. So the power electronics industry has been driven by three main drivers. Mainly you can see here, so electrification. So it's clear now that this trend is touching everything in our daily life. So everything is becoming electrified. Mainly like cars, that's the best example that we can have. We moved now from internal combustion engine cars to electrical cars. It's becoming like something very common. If I said it like 20 years ago, it won't be like took me like a fool. But now it's a reality, and it's even replacing the ICE cars. So efficiency also is another driver for the power electronic industry. So now we see more and more regulation to impose higher efficiency, less power losses. And you can see it even in Europe, more and more regulation are being set. Like, for example, the regulation for the data center power supply that has been effective since January 2023. So there is a clear trend toward high efficiency and less power losses. And of course, sustainability. So here for sustainability, it's aligned with efficiency and electrification. So sustainability, one of the main objectives is CO2 emission reduction. So all the governments now and companies have plans to reduce CO2 emission, to have what we call the neutral carbon neutrality. And that's a goal. Like even in Europe, we have this goal by like 2030, and 2035. So all this you can see here. So the major, let's say, goals and trends is to lower the energy consumption by better efficiency and to lower the CO2 emission. So to put it more in a historical perspective, so we can see in the 70s the electrification and the power electronic industry started in the industrial world with automation and the use of more electrified machine, and then it moves to the mobile and consumer area. So we see like more and more like the smartphone, the consumer electronics now are a kind of commodity. Of course, it has a small slowdown because of the COVID and the lockdowns in China, but still it's a multi-billion, tens of billion of market. And last but not least, so automotive and mobility. So as I explained first, so in the previous slide, so all this target and incentive from the government and regulation to ban the ICE cars. So all this aspect has pushed toward the electrification of the automotive industry. And when we say electrification, it's the usage of more power electronics. So we need power electronic device, either silicon, gallium nitride, or silicon carbide. So here we put the three technology or the three choice that we can have to use for power electronics. So you can see the gray part is still the biggest part. So silicon is still here and will remain the biggest part of the power electronic industry. That is can be valued like around 30 billion by 2028 of the power electronics industry. Nevertheless, wide bandgap material are emerging and taking more and more share from the silicon business. You can like see it's started already back in 2017, and it's taking more and more share, profiting from the EV business. So now you all know that SiC it's well adopted in the main inverters for the cars, which are started with Tesla, of course. And GaN is started and took off with the consumer application. So now, especially in China, it's coming and it's becoming kind of commodity to have a GaN featured charger. Everyone, even that didn't have PhD or didn't know about GaN, can know about GaN. This word is already like something known, especially in China, because the GaN charger are kind of commodity and very common. And then GaN, of course, will not stop there. So it will expand to other application, what you call like high power, high end application compared to the consumer power supply. And it's like the wide bandgap. If we take it in total, we expect that it will exceed the 30% share of the total power electronic industry. So let's now move to the power shape. So that's the most recent data that we have. It comes from our recently released report, the PowerSeq 2023. And you can see here the evolution of the market from 2022 to 2028. So the CAGR, you can see it's you have a 31% CAGR, which is impressive 2-digit CAGR. And it's clear from the graph that the orange or red part are the dominant driver of the power SiC market, which is the automotive. So as I said, so the SiC now is widely used for inverter. It started when Tesla made the move with ST microelectronics and released the first SiC featured inverter in the Tesla model. And since then, there was like this wave of adoption of SiC. A lot of OEMs, car OEMs, has followed this trend, and you will see it in the coming slide how big and how important this industry is become. For sure, the SiC will not only be applied for automotive. It's also applied for industrial. You can see this dark blue segment, which is getting also bigger. So industrial application here, we put fast chargers, so charging infrastructure are included in the industrial segment. We have also other applications like motor drive for industrial use. So SiC is also considered for industrial application. And of course, for energy here, when we put energy, it's the photovoltaics. So in the inverters for the big solar plant, we need SiC. So here, just to specify and to define a little bit more what we say about and what we include in the device when I say power SiC device market. So here we consider 4 types of devices which are accounted in our model. So of course we have the discrete, we have diode. When we see SiC, we have diode. We have transistor, so MOSFET, and we have also models, which can be full SiC model. That's mean a model that made only with SiC, or hybrid model, like model that contains, for example, silicon IGBT or silicon MOSFET, and some diodes, SiC diode or SiC MOSFET. So we take into account in our model all these 4 types of devices. And you can here see the split in terms of the device type. Again, this graph comes from our recently released report, PowerSiC 2023. And you can see that the total full SiC model will dominate the PowerSiC device. And this is, of course, thanks to the EV application in the automotive. So most of the inverter that feature the SiC will use full SiC model. So that's why you see that the biggest share here it's coming from SiC. And discrete, as you can see here, so discrete will be can be used in other applications like onboard chargers, like industrial application, EV charger, and other applications. Well, because there the power doesn't need really to use power model. So for the inverter, we speak about hundreds of kilowatts, where we need really to use SiC model, power model. But for OBCs, for example, OBCs is less than 22 kilowatts. We can do it with discrete devices, and same for other applications. So SiC, it's as I said, it's mainly used for the automotive business. So here I put a little bit higher view on this business to give you more context about the automotive business. So here you can see the split in million units about the different type of cars until 2028. And it's clear that you can here see like the blue, dark blue part is getting more and more share, which correspond to battery electric vehicle. So battery electric vehicle that they don't have ICE, and that's the target in the future, so to have only battery electric vehicle. But of course, we will still have the other type of electric vehicle, and I will explain the difference in the next slide. So between the mild hybrid, plug-in hybrid, and the other. So if we see, this trend will also benefit to the more penetration of SiC, because SiC devices are meant for mainly for battery electric vehicle, where we have like electric engine, and we need really to implement the SiC there. So that's the chart which classifies the different type of cars. So here we have the ICE with the CO2 emission. And then we have what we call XEV, so which can be mild hybrid with a 48 volt system that combines just small motors and it's mainly with gasoline. But here the idea is to have less CO2 emission and less gasoline consumption. Then next transition from mild hybrid is the full hybrid. So here the power, we speak about higher power, and but still we still need like the ICE. So the cars have inside like ICE motor and electric motor. And the transition from full hybrid, it's the plug-in hybrid EV. So same here, you still have the gasoline, but you can charge from the grid. So the difference, like full hybrid, there is no like onboard charger or way to charge. But for the plug-in hybrid EV, you can have the possibility to charge the car from the grid. And then of course we have the BEV and the fuel cell. So that's we consider as a small segment in the automotive industry. But fuel cell are the cars that function with the hydrogen cell that we consider as like a small segment in this industry. Okay. So speaking about PowerSiC, I already mentioned the beginning of the PowerSiC, and they took off in the automotive industry. So all started with the Tesla Model 3, when Elon Musk had this crazy idea to implement SiC, thanks to ST. So they took the risk to implement the SiC, because we know the automotive industry is still a conservative industry. So the adoption of new technology is not straightforward. There is a long development time. They have to make sure that the reliability is there, and it takes too long to make the move and to adopt. But Tesla, as a startup, American startup with a crazy CEO, so they made the move, and it was successful. It was a success story. So and then you can see from 2022, like the number of OEMs that already are following this wave, like Hyundai, Chinese player, some other startup, like you see the American startup, and also of course European OEMs have also would like to release the EV cars with SiC. I think I will not spend a lot of time on the driver of SiC, but you all know that the advantage of using SiC compared to silicon. Here more details about the design win. So in the previous slide I mentioned some names, but here you can see in this table who is supplying to who. Most interestingly is onsemi, who is doing a great job to secure design wins with different players. So onsemi, they have this target to reach 1 billion revenue this year. So if they want to have 1 billion, they need to have design win and to supply to multiple OEMs, to multiple customers. ST has been the first to has been pioneering this industry, and is still the leader of the PowerSiC business, thanks to the supply to Tesla. But they are also trying to extend their customer database, of course. And we have Infineon. They are announcing some partnership, and Wolfspeed, of course. So Wolfspeed, they are the pioneer and the leader in the wafer supply. But in the recent year, they are going up in the supply chain to supply devices and even models. So you can see they are being successful to gain some design win. And you can see the most of the color here is GaN, so it's mostly for inverter. And of course, SiC can also be considered for onboard charger and DC-DC converter in the car. Okay, so one trend in the automotive that I want to highlight here is the 800 volt platform. So it started 2 years ago to speak about this kind of platform. So previously what we had, it's a 400 volt battery system. But in order to have what we call the fast charging and to have extending range, One of the key solution here is to go to 800 volt battery system. And what is shown here that the move to 800 volt system is even beneficial and more advantageous to SiC. So you can see it here in terms of cost and the performance difference. Because in the 400 volt battery system we use 650 volts. So you can see in terms of cost, the SiC doesn't really still expensive. It's more specific in the system level side. And of course in the device side, but moving to the 800 volts battery system, we will need 1200 volt, and here the added value of SiC, it will be more pronounced compared to silicon. So the performance, you can see the performance, it's even better, the delta compared to the 400 volt battery system, and in terms of cost, we will have less delta. So it's more justified the use of SiC when we move to the 800 volt battery system. And here we already try to have a forecast and how the 800 volt share will take in the total car sold. And you can see that the 800 volt it will be taking more and more share in the future. Still, the main platform is for 400 volts. But a lot of car makers are already adopting the 800 volts. So namely Hyundai. So Hyundai, they already released the platform they call EMPIR platform, which is based on 800 volt system. And other car OEMs, as you can see here, they already have the roadmap and the plans to switch to 800 volt system. So now let's go to the supply chain. So that's let's say an overview of the supply chain. It's a typical slide that we always show for the any kind of supply chain we have in the industry, and that's related to power SiC. And you can see it's there's a lot of play in this industry. They are trying to take advantage and take share of this power SiC, mainly in the automotive. First takeaway from this graph that the power SiC industry is mainly driven by the IDM business model. So IDM, it means integrated device manufacturer, or vertically integrated device manufacturer. So that means that, for example, one player, they do internally everything. So for example, if you take the case of Wolfspeed, they do the bowl internally. They do the epitaxy, the processing, the design of the device, and then the model. So that's what I mean by IDM business model. So we see it more and more. So it's clear that the power SiC industry is dominated by this business model, where all the players they want to keep everything internal as much as possible. But nevertheless, we still have some kind of what we call the fabless model. Which are players, they have the know-how and the IP to make device, but they rely on foundries and on substrate providers for their production. And even more interestingly, that we see like Tier 1 and system maker and even OEMs that are going down to the supply chain. For example, Bosch, they are investing, and now they are even able to make the chip internally. We have even OEMs, car OEMs that are going down to the supply chain. So in one word, that what I can say that power SiC is really disrupting this ecosystem and the conventional automotive industry, where the OEMs are in their place, and then there is the Tier 1 and there is the Tier 2, the component supplier. With the EV industry and the power SiC, there is a kind of change of paradigm and in the power supply. And you can see it here. Now we speak about car manufacturers that can do the SiC epitaxy. It's something that we could not imagine before. So, and that's come, of course, with several investment that there will probably like partnership, M&As, multi-billion investment that I will show a little bit in the next slide. But before that, I want to highlight the top player in this industry. So in the left side of the slide, I put the wafer supplier. So the top wafer suppliers. So I already mentioned Wolfspeed, which are the pioneer and have the know-how and let's say the best quality, world quality for SiC wafer. Coherent, so previously 2.6. Coherent also are gaining a share and are major supplier for SiC wafer. And in terms of device, the ranking, in the top level it didn't change this year. Now ST are still dominating the power SiC device industry. As I said, thanks to their work with Tesla, so they did the first move and it was a success story. And then other players are also gaining share, so mainly Infineon, Wolfspeed, Onsemi, and Ron, thanks to multiple design wins in the automotive industry and also strengthening their business in the industrial segments. And you can see here some car OEMs who are already adopting and like featuring their car with SiC. So the total business here you have more details about like device market revenue. And when I explained first the methodology, so that's what I mean. Like for example, this number comes from the what we call the bottom-up approach. So we get this number from aggregating the revenue. So this work comes from what we call the bottom-up approach. And you can see like the growth, the impressive growth of the power SiC business, like 71%, 2021, 2022. So even though with the COVID, with all this economic letdowns, like that all the world went through in the recent 2-3 years, the automotive business didn't really be affected. It wasn't affected with this situation. In the contrary, if you see the global picture of the automotive business, it's even increasing, especially in the EV segment. So so I showed like a lot of people that are coming to this industry and investing, trying to secure their position and to have the biggest share of this industry. So here I'm putting some recent announcement about M&As and partnership from some players in the industry. So here, you know, at the equipment side, SAM, the purchase, the acquisition of LPE, and EMPIR also acquired by Vico. So those people, they want to have to secure the equipment supply. So for the epitaxy. And then also we have seen some M&As at the device level. So the recent acquisition of Genesis, which is the fabless company, which is acquired by Navitas, also a fabless company. So Navitas is previously was a main player in the GaN, power GaN, but by the acquisition of Genesis and also acquisition of other silicon-based driver company, now they define themselves as a new generation of power electronics company. So it's kind of kind of strategy to have access to GaN, to SiC, and also to the driver, silicon driver that come with that are needed with for the power SiC and power GaN operation. So in terms of partnership, the main idea here is that all these players here, they want to secure the supply of wafer and of device. So they are trying and more pushing towards signing LTA, long-term agreement with suppliers. And here we hear like astronomical numbers, like billions. For example, Renesas, they announced around 2 billion investment for Wolfspeed. We see same numbers like from Vitesco and other players. And one interesting thing here that we see more and more Tier 1 pushing toward partnership with device supplier, because the specificity of power SiC is what we have seen previously and in the previous years, that mostly car OEMs that coming directly to the device supplier, the Tier 2, like Tesla, Tesla and other. But here we see more and more Tier 1s being active and trying to get their positioning and their market share there. So lastly, I will speak a little bit about Soitec. So for sure, we all know. So I think we had this presentation yesterday with Soitec. ST, they are publicly announcing that they are supporting the technology, the SmartSync technology from Soitec. they announced that they will be using it especially for the 8-inch transition to 8-inch. More interestingly, also is this announcement of the joint venture formation of ST and Salman. So ST, they are now also investing in China. So Chinese business also, I speak about the world global view of the automotive business, which is booming, and it's even more booming in the China. And some players are taking strategic moves to secure their positioning in the Chinese industry. So here more investment, more capacity expansion in this slide that you can see. Again with big numbers, like billions of numbers. So it's a direct argument that the power SiC industry it's not something marginal. It's really taking off, and it's a multi-billion market, as I showed in the first slide of power SiC. So it will reach 9 billion by 2028. And to support this market, we need to put investment, to put money on the table, and to construct fabs. As you can see, like ST, 730 million euro fabs in Catania, Infineon as well, and even in Asia part also. So Rom, Mitsubishi, also is investing, Wolfspeed. So all the big players that I showed in the supply chain slide and the ranking are already putting money, making investments. And of course, you can see here, it's also announcing my transition to 8-inch, because I will speak a little bit about the 8-inch transition from the SiC wafer. So that's the evolution of the wafer size for SiC. So as I said, Wolfspeed has been the pioneer for the SiC wafer. So they have a long development time and expertise in SiC wafer production. So started when it started the SiC industry, it has been mainly for the N-type SiC wafer for power electronics with 6-inch, and it's still 6-inch dominant. However, we start now to talk more and more about the transition to 8-inch. Now since 1 to 2 years, there is more and more interest and investment toward making the 8-inch SiC wafer. So still it's the beginning. So with Wolfspeed taking the lead in terms of development, but of course other players are trying also to develop on their side the 8-inch. It's not an easy task. It's very challenging, and yeah, I think I can speak a little bit about the details in the next slide about how it's challenging to make the 8-inch wafer. Before that, this slide it's explain also one main aspect and concern in the power SiC industry, which is the supply of SiC wafer. So it also aligned with, I said previously in the previous slide, with the 8-inch. So now with more adoption of the SiC in the EV industry, there is a need of supply. So the demand will increase, and the supply should follow. And just here, what we are showing is it's the analysis on what we have. So the red bar is the wafer demand based on your forecast. So when I said based on your forecast, it's based on the top-down approach. So what we do with our model, with what I said, like we start with the end system, how many cars we have, and we go down to how many wafer we need to supply these cars. So with the forecast, of course. So that's, and of course we here in the model where, of course we implement in the model, we feed the yield, we feed the die size, we have all these parameters that we feed into the model to get to these numbers. And then we have the front-end capacity in orange. So here it's the process side. So what the capacity in terms of processing. And in the green bar, it's the wafer capacity. So how many wafer start, like how many wafer, like that. And just the two, like the orange and the green, are coming from the public announcement and our top-down approach. So not only public, because we have also access, as I said, to all the players in the community, and they trust us, and we have like a close communication to be able to aggregate all this data and to make this type of graphs. So the green one is the wafer capacity, and we put in the light green what's if we add up the Chinese announcement. So I again stress on the Chinese industry, especially in the power SiC and the AV, which is really booming, and we see a lot of more and more players that are entering this business and even getting better in terms of supply capacity and quality. Like for example, SiCC, we already recently heard that Infineon, they had this FTA with SiCC. That means they reached the good quality. If a Chinese player that gets validated by Infineon, that means they have a good quality. So just here, the question here: are we getting to a shorter situation in the future? So just seeing this graph, we will say no, but we have to take into account here the yield, the utilization rate, all this stuff, because here comes from announcement of the players. So they will announce 50K wafer per month, but is this 50K wafer per month good wafer? If this 50K wafer per month meant for automotive, MOSFET, for diode, for is there some internal part that will kept for R&D purpose? So the concern of shortage is still there, and that's also explained the investment and the capacity expansion that I showed in the previous slide. And we are keep watching this closely, and we have in-depth analysis, more in-depth analysis on this aspect, and especially in our monitor server. So it's a quarterly server that we really follow on a daily basis this aspect, and we try to answer this question of shortage in the future. So yeah, so that's, I think we'll have 2 slides. I don't know how much time I still have. 15 minutes? Wow. So I think I will skip this because I have this PowerElec part. So here just to have you quick outlook on the technical aspect and the challenge. I think it has been already discussed during the presentation before. All this aspect of planar or trench devices in the Bosch presentation this morning was about packaging, and I spoke about the growth and wafering, especially when transition to 8-inch. It's also a kind of challenge and bottleneck here, and there is a lot of work which is done here as well as in the epitaxy side. So I will go a little bit more rapid. So for the wafer, I wanted here to speak about innovation in terms of wafering and wafer production, like transition to 8-inch, Soitec, also the wafering method.
Take your time. It's
yeah.
We're not in a hurry, so just forward.
Thank you. Take your time. Thank you very much. Yes. Yeah. Because it's very interesting, and I really want to discuss this. So yeah. So let me go back a little bit to this. sorry. Yeah. So yes. So I mentioned this part. For example, for silicon now, it's kind of we call the dirty business, or really it's a separate word to make the ingots and to go to the silicon wafer, which is a commodity. But for SiC, it's not this. It's not the case. It's not a dirty industry, because we need a good SiC wafer to have a good epitaxy and a good device. So the boule, and I can say even the powder matters here. So we need really to go to make sure that you have a good powder to make a good boule, and then to make a good SiC wafer. So this part of the processing, it shouldn't be neglected, and we see it already in the industry that a lot of people they put money and a lot of effort here. And it's very important for the 8-inch, because to make a boule you need the seed, and access to the seed it's on the ground. So when you have access to the good seed, you can make the good boule, and then consequently a good epitaxy and a good device. Yeah, that's I say that I will speak a little bit about the 8-inch challenges. So one of the main challenges is to have the seed, the good seed for 8-inch. So and it's not a 1 month work. It can be like years of work to make a good SiC, because a ball will take like in order of 2 weeks to get for 6-inch ball. 8-inch might be more time, like to get a ball, and then you have to cut and then to assess and to have this feedback loop, and in order to until you optimize and you have the best seat. So that's very important. Of course, the equipment here are important aspect. So the transition to 8-inch, you need the equipment that support 8-inch. This work is already ongoing with the equipment manufacturer and the equipment supplier. And of course, going from 6 to 8-inch, you have to scale up the process. So here, scaling up the process also, it's not a one-day work. You need to take into consideration all these defects and removal of the defects and reducing of the defects. So it takes time to optimize and to go from 6 to 8-inch. So there is a lot of work that needs to be done. But it's a question of time, what we think. Nothing is impossible. So technically, there is no challenge. So it's just need the time and the people to do it. For processing, I think I will not spend a lot of time. So we have two types of device, like trench and planar. So planar, obviously, they are less complex to do and simpler. A lot of players already like start with the planar device and like try to also to improve this kind of topology. But they also have in the map to make the trench, because the trench, the main advantage to trench, and you will have smaller size, so device will be smaller. You will have a better RDS-on also in terms of resistivity in gain. So and when you say smaller device, we'll have more device per wafer, so we need less wafer, and it's aligned with the demand and supply concerns. Yeah, and the packaging, so I think Bosch already spoke about this like new type of die attach, novelty and innovation in the packaging side, which is also very important in the power SiC, because for power SiC we need module for inverter. And power module, you need to optimize, and the thermal management, mechanical aspect, electrical aspect. So the epitaxy, of course, I already spoke about epitaxy, but we need to optimize, and it's a high temperature, so 2000 degree or like in this range of temperature growth. It's a high temperature process, means it's costly process, and it's a very sensitive process. So to have like the throughput and run-to-run uniformity, it's a challenge. So it's a day-to-day work. So going back to the innovation, so I already spoke about 8-inch, which is already an innovation to transition from 6 to 8. It's not just a change on the number, as I said, it's years of work, and we see it already with Wolfspeed and the other player that already developing 8-inch wafer. Engineering SiC substrate, so here I mentioned Soitec, but there is also Cycops in Japan, who have this idea about transferring a thin micrometer thick layer to a foreign substrate, a polySiC substrate, polysilicon carbide substrate. So here the idea is to reuse the good wafer. So once you have a good, let's say a 500 micron thick wafer, you can reuse, so by splitting. So Soitec, they have, we all know how this smart cut technology. So they know how to split micron thick layers, and they know how to bond it in a foreign substrate. So they have the smart SiC and smart bond technologies, patented technologies, and they first applied in the silicon insulator, which was a success, and now they want to replicate it in the SiC case. So wafering, we have Infineon with the cold split technology, Disco with the carbide, laser-based splitting technology. So here is the idea here from the SiC bowl, how we get the most of wafer. So we need to have the less scrap, and all this, for example, this player are trying to make techniques that instead of having 10 wafer by bowl, we have like 15 or 10, 20. So KISAB, it's another approach for innovation. Here it's how to make, it's making the ball. So here they have this fast sublimation technique instead of PGT technique to making the ball. So PGT is physical vapor transport, which is the conventional and main technology used to make the ball from the powder. But KISAB, they have kind of their, developed their technology to make the ball, which can make better quality balls and having better throughput. Yeah, just a photo from Yole System Plus, the take-down photo. I already explained like the planer and the trench, like two type of solution to make the devices. And yeah, you can see like the complexity is obvious on this two photo. Here you need to make the edge. You need to get a good side walls. You need to deposit the dielectric. But here it's just like doping, and no trench, no like a gate oxide. And here like very controlled gate oxide deposition. So I finished with PowerSiC. I think I will have 1 more hour, so please stay with me. Okay, because PowerGaN is it's also a very interesting topic. It's not less interesting than PowerSiC. So let's speak about PowerGaN. PowerGaN, as I said in the first slide, was the overview of power electronics. So it's dominated by consumer application. So consumer here, it's mainly fast charger. So now we all know that GaN is good for fast charger. Fast charger with GaN will be smaller and will heat less and potentially same price or cheaper than silicon-based power supply in the future. But GaN will not stop in the consumer. Just coming back to consumer, so it's not only fast charger, of course, so, but fast charger is the biggest share here. Consumer also, there is home appliance, there is Class D audio application, there is other consumer application, but power supply is the main one. So GaN will also go through another wave of growth in the future. As you can see from the black circle here, it's automotive and mobility. Which is expected to be the next wave of growth for PowerGaN. So when we see automotive and mobility, it's not only powertrain, it's not only OBC, DC-DC inverter. So automotive and mobility here, it includes other applications like automotive LiDAR. So we know that LiDAR, PowerGaN device can be used as a LiDAR driver. Also for mobility, like we have e-bikes, we have light electric vehicle, two-wheeler, three-wheeler. So it's a big segment for PowerGaN. And also we think that telecom, and we understand that telecom and infrastructure, and here mainly data center application will be also a driver for PowerGaN in the future. So again, with the efficiency story and all these regulations, so now we have a new regulation in Europe that imposes the use of kind of efficiency in power supply, and this will be beneficial for PowerGaN. And the PowerGaN industry will reach, we expect it to reach 2 billion by 2028 with, again, an impressive CAGR, like 49% CAGR. So CAGR is a compound annual growth rate. As I showed for the PowerSiC, so here for PowerGaN, what we consider as a device. So we have kind of three categories of device that we consider in the PowerGaN device market. So we have what we call the discrete. So discrete here, that the package device come in the package device come with only the GaN switch. But here we have a small exception for the cascade mode. When we need to use the silicon, we have a D-mode, the GaN, and we need to use the silicon to make it normally off. And then we have the system in package. So here we have in the black box, you will have the bare die, the hemp die, and then you'll have some drivers. And then we have the system on chip, which is a monolithic solution. And in the GaN device industry, we consider silicon and sapphire substrate. So we know that now commercially available device, we have mainly GaN on silicon, but we have also GaN on sapphire. So, and that's the split between all this type of device that I've shown. So this discrete has been is taking more share, and then we'll have the system in package, system on chip. So the discrete solution offer better flexibility to the system designer and system maker to choose their own driver, to choose their own features. And the system on chip and system in package, they offer a faster time to market. So, for example, in consumer context, where the development time should be in the order of like 3 to 6 months, you don't have time to design and to choose your own drivers, your own topology. So you need really a time like a plug-in play solution. So here it's really the system on chip, system in package. But you don't have a lot of flexibility in terms of design and like at the system level. And for, yeah, that's make more the Ghent discrete solution more favorable, especially in the high power, high end application, where the design, the system maker, they need to put more effort in the reliability issue to guarantee that the GaN-based system will work like in the right way. Yeah, so that's, I will have some slides that will explain a little bit the market application. So as I said, so the power supply, GaN power supply market is the main one. And you can see like the drivers and why we use GaN for the charger. So we need to get to this desired corner when we have like the most possible small charger. And you can see it here. Exactly, I put two examples like it's the same charger made by silicon and by GaN, and I highlighted here the power density gain when you use the GaN charger. And you can even find better example than that, because here it's apple to apple. We have like same type of charger, same level, same power level, and yeah, you can see like already the power density increase using the GaN. Yeah, so GaN charger, I already spoke that it's kind of commodity now, and you can see it from here, like the number of design wins since 2022. And this is not exhaustive list, so you should know that there is even more charger that comes with GaN. And here I want to highlight three points. So first is that all the consumer OEMs have already adopted GaN. So we can see it here from the logos. Even Apple have adopted the GaN. Second point that we are seeing a transition or a trend toward high power charger. So more than 70-watt charger. That means that with high power charger, you will need to use more GaN device per charger. So that's increase the GaN content and increase also yeah. So that's the main conclusion. So when you go to higher charger power, you will need to implement PFC, and also you need to use like higher content of GaN. And the third point is the entry. We see like it's kind of now a strategy in the power GaN industry to enter through the consumer power supply, to enter the industry by the consumer power supply door. So you see like more and more Chinese player, like here I'm putting some example, like already having design win. Those are Chinese players that already profiting from this business and having already like design wins or fast charge and fast charge. Please. Of course, here the Infineon are not here, but you know that Infineon acquired Ghent system, and I think once the acquisition will be validated and completed, we will remove the Ghent system logo. There will be only Infineon. For automotive, so here I'm putting some work and partnership for automotive. So it's not a new thing for GaN. It has been already GaN for automotive. It has been especially in powertrain. So here I'm focusing on the powertrain side. So powertrain means traction inverter, OBC, and DC-DC converter in the car. So you can see here the number of tier ones that are already involved in the power GaN development for automotive. So it has been already considered for decades now, but it takes time. As I said, so automotive business is conservative industry, and they don't change technology overnight. So they need to do a lot of development time. Like for example, Vitesco has been working with GaN system now since more than 10 years. Same for other players, and for automotive, we have already automotive qualified GaN device. So we have seen in the previous presentation this AEC qualification process. It's already applied for GaN, and it's already commercial. We have, like for example, GaN system and transform. They already have automotive qualified GaN device commercially available. So it's already a step down toward more adoption of GaN into the automotive business. One final thing about the application is the data center. So I mentioned the telecom and infrastructure. So for data center, as you can see here, so it's about efficiency, and it's not only about efficiency. So even you can see here from gas system, they showed some numbers, and it's kind of sustainable business for data center own. So when they will adopt the GaN, they will comply with the regulation, and they will also have less consumption of energy. That means less bill of electricity. So they will gain money also because they will have like less operating expenditure. So it's kind of a win-win approach when adopting GaN, but still some reliability concerns, especially from system makers. Even though some system makers already made the move and adopted GaN, like you can see here, Bayer Power Solution, Delta Electronics, they already adopted, and they have commercially available power supply for this data center with GaN, especially Bayer Power Solution, which is working with Transform, and others are following. We have seen recently the announcement with Lition, and working with Texas Instruments on power supply for data center. And so I mentioned the power supply, but it's not the only application for GaN in the data center. GaN can also be applied, and mainly low voltage GaN, or less than 100 volt GaN device, can be applied in what we call the intermediate boost converter, which is basically a DC-DC converter that will convert the 48 volt output of the power supply with a 12 volt, and then to go to the loads, so the servers and the CPUs and memories. So the supply chain, again, the same slide, but now for power GaN. So you see fewer players than power SiC, but it doesn't mean that it's less interesting. It's also a very important business for power GaN. So in contrast to power SiC, you can see that the power GaN ecosystem is mainly dominated by the fabless business model, where I put here. So you can see all the main players like Navitas, GaN System, mainly Navitas and GaN System, they follow the fabless business model. That means they don't own a fab, so they have the IPs, they have know-how to make the HEMT device, and then they go to the foundries to make the production. So in the case of Navitas and GaN System, the main foundry is TSMC now. So the main GaN foundry as of today is TSMC. But of course, we have other foundries that are also doing business in the power GaN industry. I can cite EPC, which is a Taiwanese foundry, which belongs to the holding with EPI. So EPI, they do the epitaxy, and EPC, they do the process. And they work mainly with EPC, and historically, but also they can work with other. Speaking about open foundries, we have BELGaN. So BELGaN is a Belgian foundry, which has been created in January 2022 by acquiring the GaN activity of Ensemi. So they are using the facility, the old facility of Ensemi for GaN, and also X-FAB. So X-FAB is also one of the main players for power GaN foundry, and others. Of course, IDMs, they are not neglecting the business. So you can see IDMs are also present in the supply chain. ST, Infineon, and of course Innoscience. Now I think we all know Innoscience, the big GaN IDM, Chinese IDM, which is extending its presence. We know that your European office is already it's in Belgium here, and they have also American office, and they have office in South Korea. So they are expanding worldwide, and they are becoming really now we consider as the top player of the power GaN device industry. So we still, in this side, especially in the automotive business, we are still waiting for the player who will do the first move to adopt GaN in the automotive. It's not anymore a question of if, but it's really a question of when. So we're really waiting. So regarding this development time and all this stuff, and the acquisition of Infineon, of GaN system by Infineon. So we have a lot of signals that that automotive, GaN automotive business will take off soon. Again, so the ranking of the top players. So I already mentioned InnoScience, but also Power Integration, which is doing GaN on Sapphire, and it has been also very active in the power supply business. Navitas, EPC, and GaN System are top leader of the power GaN, and that's according to our estimation. Of course, always emerging business that brings money, that have 49% CAGR. It will bring more investment, more interest, more money, and we can see it here. So we already counted with a quick math. We counted more than 4 billion investment since 2019, and here we are putting some highlighting some of them. And of course, one of the biggest highlights is the $830 million acquisition of GaN system by Infineon. Here we also have some analysis that we are putting also in our report, is to explain why Infineon has purchased a 20 million size startup company for $830 million. Is it is that justify the price or not? So there is kind of analysis that we put also to on our side, on our understanding to of course Infineon they didn't make it. They know what they do, so if they are purchasing this company for $830 million, that means they know what they do, and there is a reason behind. Of course, and then in China also there is I mentioned China's business, so you can see especially in science they have been backed with private investor in China, and they also profited from the government support to make this pure GaN IDM, which is a unique. It's a company that's saying the word. In terms of technology, I will be fast. So GaN has a multitude of solution. Like to make GaN, you can make it depletion mode, enhancement mode. You can make GaN on silicon, on sapphire, even on other substrates. GaN can cover a wide range of voltage as compared to SiC. SiC is more in the high voltage side, but GaN you can see you can even have 14-volt GaN devices, and it's already deployed. I didn't speak about it, but in the other voltage protection application in smartphone, you can use 40-volt device. So now GaN devices are even into you can find it into smartphone, not only in the charger. In the smartphone electronics, you can find the GaN device. Still, it's the beginning, but it's very promising application. And then at the system level, of course, integration I already mentioned, like the discrete, the system in package, and at the system side and the end user, of course, there is all this reliability and standard aspects and the system make. So I think we mentioned also in the previous presentation. So GaN switch very fast. So it brings it imposes new ways to design system. It cannot work with the old ways in some cases when you have 20 kilohertz switching silicon MOSFET. With a 1 megahertz switching device, it's not, you cannot apply the same things basically. You need to do some work, and that's the design side. So system maker, they need to do work to take into account all this EMI issue and other side, on the other aspect. So here that's a quick comparison between GaN on silicon and GaN on sapphire. So it's mainly the keyword here is lattice mismatch and the thermal conductivity mismatch. So with silicon, the lattice mismatch is higher, so we need to put a buffer layer and to make to accommodate the lattice mismatch and to have the less defects. But you can still see from SEM image there are some defects. For the sapphire, the mismatch is less, so the buffer here you need less constraint on the buffer. So only a few nanometer of aluminum nitride layer is already good to make a good quality GaN, or even a low temperature GaN buffer can work. So you don't need this sophisticated, fancy super lattice layer. And you can see here some comparison. I think I can go through a beginning. D mode and E mode. So intrinsically, HEM devices are D mode because it's based on 2 decks. So it's basically the terminal voltage is negative. But in power electronics, we need when the voltage is 0, we need 0 current. So it's for that's the power electronics. So that's safe. So we need enhancement mode. So normally off device. In general, so normally off device, that what I said. So when the voltage is 0, we don't need current flowing. So when we have D mode, which is the straightforward way, we need to make what we call the cascade topology. So we implement the silicon MOSFET to drive the gate and to make the terminal voltage positive. And there is some other ways to make it also normally off, which we call the direct gate drive. For E mode, there is 2 ways basically. So there is we add the P-GaN layer, or we have the mishand with the research gate. So that's the 2 ways to make the enhancement mode. For packaging, same. It's have multitude of packaging proposed for GaN from TU, which is the most standard, let's say traditional type of package. We have also embedded die package, and we can also find the wafer level state package, especially for low voltage device. But the most of the packaging are mostly SND package or TUL, so TU leadless package. And the final slide, I think here for the power GaN, it's just to mention, I mentioned GaN on SiC, GaN on sapphire, which already in the growth phase, but we have also some kind of emerging and close to commercialization type of device, like GaN on GaN. So now we hear more about vertical GaN devices. We hear about GaN on QST. So QST is a type of device proposed by a startup company called Promise. Here the idea to have, I spoke about lattice mismatch, the previous issue, the constraint when we do this heteropitaxy. So the KST substrate main goal is to eliminate this issue, and also take into account that it's isolated, it's electrical isolated substrate, so it can be beneficial, same as SY for all this system on chip monolithic integration. So it can remove all this crosstalk issue when you have a conductive silicon wave. And then I mentioned some other emerging like gallium oxide. So we have wide band gap, but we have also ultra wide band gap. So not only, so that's the next. So after wide band gap, now it's more in the research area. We speak about ultra wide band gap material like gallium oxide or also diamond. So those are areas of R&D that also will be probably in the future, like we'll speak about it in this area. So the conclusion here, so just two slides of conclusion and then some slides of related report. So for SiC, as I said, so we started with automotive business, and it's getting more and share of the automotive business. So 800-volt technology, some high-end, high-power application, DC charging infrastructure, which is becoming more and more trendy in the power SiC industry. For GaN, so it's consumer power supply. It will stay consumer power supply, but it will also have another growth engine like EV, data center. And in the future, we estimate like GaN can even with better maturity, with better acceptance, with more supply chain maturity, we can have GaN in, because there is no reason that GaN will not be applied in other applications. So GaN on silicon, GaN on sapphire as of today, and probably other platform in the future with also 8-inch coming soon. So all these slides are based on our reports, mainly power SiC, power GaN, and other also reports like status of compound and power electronics for mobility, electric mobility. So all these reports are already like I inspired my presentation from this report. From the chip down also, that's the chip down that I spoke about it from Yole System Plus. And we have also the monitor service with the direct access to the analyst. So it's a quarterly based service. So here we have one dedicated for power SiC and power GaN. And you can see the company that we follow quarterly base. We follow their earnings calls, we follow them, and we follow their activity. Same for other topics in the compound semiconductor team. And with that, I would like to thank you for your attention, and I'm happy to answer your question. And I think I took more than one, but yeah, thank you very much. Thank you.